Just a reminder for everyone to mute their phones at this time. Welcome to the second of our webinar series, which was actually done originally on March 10th, New Developments in Environmental Site Assessments. My name's Alan Hahn, and I'm the Business Development Manager at Dragon. And we would ask that if questions during today's webinar, that you email them to me. My email is up on the screen before you. It's ahahn@dragon.com. As I'd mentioned, this webinar was originally done on March 10th, so this is a reprise of that webinar. Today's presentation will focus on some of the tools that can help you build a robust conceptual site model to better understand soil and groundwater conditions at your site. And today's presentation will be handled by two of my colleagues, Christopher Perret, who will talk about some of the advancements in direct push technology and gathering real-time data, and Dr. Michael Sklash, who will talk about some more advanced scientific methods. And with that, I'm going to turn the presentation today over to Mike.
Hi, I'm Mike Sklash. I'll be doing most of the second part of today's webinar. My background, just really quickly, is bachelor's in geological engineering with master's and PhD in earth sciences from the University of Waterloo, where I studied hydrogeology. I was a professor for about 15 years at the University of Windsor, and I've been an adjunct professor at Lawrence Tech in Southfield, Michigan for the last several years. I've been senior hydrogeologist at Dragon since 1992, and in general I work on expert projects, more larger and more complex projects in the United States and Canada. So this webinar, as Alan said, is really, it's the first part of a two-part series. We're going to talk about conceptual site models and how you get the information for your conceptual site model. That's what we're going to do today. The groundwater remediation webinar was on a couple of weeks ago, as Alan said, and you can find it on YouTube. You'll be able to find a link on our blog page for that. So what is a conceptual site model? That's one of the things we're going to talk about over the next 30 to 45 minutes. Why is it important? And we're going to focus on some of the recent and non-traditional tools that can be used to build a more robust conceptual site model more cost effectively. And what I mean by non-traditional tools are tools that are out there which most consultants won't use. They're a little more specialized. And what I mean by more robust conceptual site model is one that can stand up to rigorous questioning from regulators and in the court and so on. So why is the conceptual site model so important? And when I started with Dragon back in the early 90s, I was thrown right into a large court battle, and I'm going to talk about that a little bit later on. But what I've learned over the years is that the decisions that are made, either on remediation, in court, or a regulator's decision, are based on the conceptual site model, not what is actually in the subsurface. So you need to be able to put together a model that the people who are making the decision can understand, and you've got to make that model foolproof. We're going to talk about some of the tools, and I'm going to turn it over to Chris Perret, who's going to start with some of the tools we use.
Thanks, Mike. I'm Chris Perret. I have a degree in geology. I'm also a professional geologist in the province of Ontario and a certified professional geologist in the U.S. I've been at Dragon since 1990. I'm currently in the position as a senior hydrogeologist, and certainly have worked with Mike on a lot of projects over the last 25 years, site investigation projects and remediation projects. So Mike had talked a little bit about the conceptual site model, and really the conceptual site model brings together all the data that you can get your hands on, starting from development of the history of a property, what chemicals were used, how long did it operate, what are the history of spills, those types of issues. The physical hydrogeology, we're going to talk a little bit about some of the tools we use to understand hydrogeology and gather geological data. Also, Mike will talk more about how to try to understand chemical distributions. We'll talk about chemical fate and transport, the sources and timing of releases or spills, and what are the applicable exposure pathways and receptors. All of these things go in together to build your conceptual site model. Well, so a conceptual site model may look like something we have here on the screen right now, is a three-dimensional block diagram where you're incorporating information at the surface, such as the location of tanks, piping, building structures, and then you're building on that downward through the subsurface. So you're taking a look at what are the subsurface geological conditions, and then also we add into this the hydrogeological conditions. And it may be that you're using a cross-section in some cases, other maps and tables, or a descriptive, a narrative within a report. So this matrix that we have here in front of us now on this slide is really what's going to guide us through the rest of the webinar today. So starting from the left-hand side, the information needed for the conceptual site model, basically we need information about the geology, what's under the ground, what are the conditions with the hydrogeology, where does the groundwater move, how fast does it move, how many aquifers are there present, what aquifers are impacted, the groundwater chemistry, where are the chemicals, what's the magnitude and extent of the impacts that have been from past releases. And then the traditional approaches, I'm going to talk a little bit about that under the geology section. Mike will talk more about under the hydrogeology and groundwater chemistry portion. And I'll also talk about some of the non-traditional approaches as we move from the traditional approaches to understanding geology to some of these non-traditional approaches. I will discuss those. Mike will discuss some of the other approaches under the hydrogeology and the groundwater chemistry section. So let's talk a little bit about how do we understand what's going on in the subsurface. Now, the old way of doing this, and it's for decades now, you would go out to a site with a large-scale drill rig like you see in the photograph to the left, come out to the site, you start drilling holes in the ground. It takes time. It's not as safe as other methods that we use nowadays. Or we come out to sites and we would use a excavator to create test pits in which we physically look at the soil and basically digging soil up and having us examine it. And I'm going to talk a little bit about how that's changed here with some non-traditional approaches. Just another few slides to kind of show you the way things have been done in the past. Again, top left-hand corner, an older style drill rig. The geologist in the top right-hand corner is in the field examining the soils, writing down the logs. It takes time and it basically is costly. The person in the field doing water sampling, a lot of data needs to be collected in the field. There certainly are new methods to do that. Geophysics, ground penetrating radar, certainly a lot of advances in the last 20 years in using that technology. And the bottom right-hand corner shows a shallow test pit that's done on a site where we're trying to look at some of the conditions with the clay-rich soils at a site. So how would we take a look at examining the geological conditions on a site. You know, in the last 20 years, the use of direct push technology has gone from very few people knew about it 20 or 25 years ago to now it's the most predominant tool used for subsurface investigations, and particularly on environmental projects. And what are the main reasons for that? Well, it's certainly safer than the older drill rigs. It's compact, it's mobile, it's versatile. We can get into a lot of situations. The amount of waste that's created is very minimal as compared to the previous generation of drill rig technology, where we had augers bringing up large quantities of soil, and in some case contaminated soils coming to the surface, in which you have to handle those soils, and that certainly adds a lot of expense. The sampling that's done with the GeoProbe is quicker. As you can see in the bottom slide, you have nice soil recoveries. These are sample liners that come in with, they're fantastic for the technician or the geologist in the field or engineer in the field to examine the soils. So it's certainly faster and more cost efficient. Some of the disadvantages with the direct push technology is that we have limitations on the depths for the wells and limited diameter of wells. We certainly can't go in and install large diameter extraction wells or purge wells for groundwater remediation systems using this technology. And some of the geological conditions do present a problem. If we run into very coarse-grained granitic boulders, for example, we can't advance tools. And we don't collect the geotechnical data that we would have collected in the past using the older technology, and that's not always necessarily needed when we're doing our environmental investigations. This is just a slide showing you how compact a GeoProbe direct push drill rig can be. This is certainly one of the smaller mobile track vehicle rigs that can be used and drive right into a building and pretty much get to anywhere we need to do our investigation. The next thing I'm going to talk about is the use of the cone penetrometer testing tools. So these are downhole tools that are advanced. Instead of going out and doing your soil borings, you would advance this tooling string that has a sensor array at the base, and it's currently now it's a wireless method, and that array sends information to a laptop in which there's software which interprets the data as it's received. And ultimately what you end up with, as you see in this slide on the left-hand side, is you're collecting 4 different sets of parameters, and the software then analyzes that data and creates a geologic log, as you can see on the far left-hand side. So this allows us to basically go out to a site and collect real-time data. We can advance a lot of soil borings using this method quickly across a site. We get detail on the geology. It's quick. We're not creating any waste at all using this method. And there's no laboratory testing because we're not collecting any soils at this point. The disadvantages are that you would have to come in with a drill rig using direct push technology, but you may have to use some anchoring devices. The field conditions may not always be suitable. Certainly that probe, the sensor that's at the end of the drill rods, can be damaged if you come across boulders again. It's expensive to replace that sensor. And again, ground truthing has to be done. So although we would go out to a site and do potentially a dozen or so boreholes using CPT, we would still need to come back and do some ground truthing where we'd go in and the geologist, engineer, or technician would drill a borehole and actually physically collect the samples just to confirm, to compare that to the interpretation by the sensor array. At this point, I'm going to turn the webinar back over to Mike.
Thanks, Chris. I'm going to talk about some of the non-traditional techniques now and within the physical hydrogeology. How do we answer the questions about groundwater movement and hydraulic connections and so on, not using the traditional approaches, but using something that might be faster and more efficient. So I'm going to talk about a technique called Hpt, and then I'm going to talk about environmental isotopes. This is a site that we're working on currently in the middle of the United States. It's a very complex Cold War era legacy site where we have a definite deadline and an important mission, and that mission is to protect the health and environment in this community of 50,000 people. There's a massive amount of TCE in the subsurface, and there are many plumes, over 10 plumes, that some of which are thousands of feet long. They move into residential, commercial, and educational districts. And what happened at this site was that the U.S. Army Corps of Engineers worked on the site for more than 15 years. The people in the city were becoming frustrated with the lack of progress of the work at the site. And they asked for a peer review of the problem and what was done. And they eventually sued the government, and we helped them with that. And they were able to get $9 million from the U.S. government, basically, to get to the end of a remedial action plan. And we've been working on the field work for about 2 years. As I mentioned, it's extremely complex. And in this conceptual site model, you can see we're working, and in this photo, in this area here, where there's interbedded sand and clay. And we want to be able to determine how far the contamination has moved. We want to make sure we're measuring the contamination in the most permeable zones of sand so that we could get the worst case scenario. And over the past 2 years, we've identified 12 different plumes. We've delineated 2 sources in the bedrock that previously in 15 years hadn't been noticed. And we're coming to the point where we've put our arms around the problem, which is important in developing the conceptual site model. We've used GeoProbe extensively, not exclusively, but extensively. We've done 13,000 feet plus of drilling. We've used HPT to guide us, and I'm going to talk about that in a minute. SP16, which are samplers that you can use with a GeoProbe. My understanding is now they've got SP22, which is a newer version. And we're going to talk about a membrane interface probe where we can get real-time chemistry. So this is the one of the parts of one of the plumes that we're working in. This is the furthest out towards the city's water supply. We're using an HPT rig, which is on the right. This is our rig that we're using for our project. Just so happens that GeoProbe, the manufacturer of the drill rig, is also on one of the other plumes at this location. And they're testing out some of their equipment right next to us. So we're getting data with the HPT. The HPT is a technique that allows us to identify the permeable zones. Then we were going to sample the groundwater from those permeable zones, while GeoProbe in their rig is using a membrane interface probe, which allows you to get real-time vertical distribution of chemicals. So this is what a HPT probe looks like. It's put on the end of a GeoProbe, and you push it down into the ground at a known velocity. The drive point drives it through the soil. This EC array allows you to get a measure of the conductivity of the soil, which is an indication of the geology. And the HPT itself is right in here, the injection port. And what happens is they pump out water into the formation, and the pressure that resists that pumping out is related to the type of geology. So if they're encountering a clayey soil, the pressure is high to get the water out. And if it's a sandy soil, the pressure is low. So here we see a log, the EC log, with depth. That's 0, and I think that's 60 feet or so. So you get a real-time vertical distribution of the geology. The further over to the right, the more conductive. That's indicative of a clay. The furthest over to the left is indicative of a sand. Here's the pressure profile with depth. And again, it's consistent. The higher pressures are needed opposite the clay, the lower pressures opposite the sand. And you actually can identify the water table, which is right there as well. So what we're trying to do is to make sure that we sample in the most permeable zones, and that's what this is indicating. That's the most permeable zone. And also you can get an estimate of the hydraulic conductivity or permeability. So a very useful device for picking out where to sample your groundwater. I'm going to move for a few minutes to environmental isotopes. And environmental isotopes are naturally occurring isotopes, meaning a variety of an atom that occur in the hydrologic cycle. And I'm going to talk about parts of the water molecule. So these techniques have been around for a lot of time. They started in the 60s, mostly in Europe, and they have been around since then, but not a whole lot of people use them. I'm going to talk about hydrogen isotopes, and specifically I'm going to talk about one of the isotopes called tritium, which is a type of hydrogen that is radiogenic, and it's got a half-life of 12.3 years. That means if you have 10 parts of tritium now, in 12 years you'll have 5. In 25 years you'll have 2.5, and so on. I'm also going to talk about oxygen isotopes. There's 2 isotopes we deal with, oxygen-16, which is the normal one, and oxygen-18, which is the heavier of the isotopes. And these all form parts of the water molecule. And I'm going to call that ratio of oxygen-18 to oxygen-16, I'm just going to call it oxygen-18. So how can we use these parts of the water molecule to help us solve hydrogeologic problems? So this slide shows you the distribution of tritium in precipitation with time since 1950 to, this is 2010. And there have been organizations around the world that have collected precipitation, usually at airports, and they conduct tritium analysis. The longest record in North America is at Ottawa, Ontario in Canada. And I've got, those are the reddish dots, and the greenish dots are an American example at Madison, Wisconsin. So you can see the profile here. In the early 50s, there was very little tritium in precipitation. That's what we call natural tritium. It was thought to be less than 25 tritium units. And a tritium unit is a special unit, which is 1 tritium atom in 10 to the 18th hydrogen atoms. This is when the US and the Americans started testing nuclear weapons in the atmosphere, and there was a progressive increase in tritium concentrations in precipitation, and that's halted in 1963 with thousands of tritium units. And the tritium concentration gradually declined with the 1963 Atmospheric Test Ban Treaty. So tritium in precipitation becomes tritium in groundwater. So we can use this input function and the half-life, knowing that every 12.5 years you half what there was there before, to get an idea of how old groundwater is. So here I've done some simple calculations that if we started in 1952 at 20 tritium units, or 25, that one half-life later, about 1964, you'd have 13 tritium units. Another half-life later, 76, you'd have 6, and so on. So any groundwater that recharged back here in the early 50s would have less than 2 tritium units in the year 2000. And then something like around the peak in 1963, where there were 3,000 tritium units, 1 half-life later would be 1,500. 2 half-life later would be 750, and so on. So you can get an idea from what the tritium concentration is in the groundwater from when it recharged. So let's look at an example problem. This is a landfill that we worked on that ended up with $100 million plus judgment. Very complex multi-aquifer site, and we're looking at groundwater flow in the 3rd aquifer. This is just a flow map showing that flow radiated out of these landfills to the east and to the south and the southeast. And the regulators who were on the other side in the court case wanted to know, or basically asserted that all of the metal impacts far away from the landfill were due to the landfill. But we didn't think that was true because the groundwater didn't flow that quickly. And how could we prove that? So this map is from 1995. So we're looking at 1995 tritium data. And this is the distribution of tritium data, with this outer ring being 3 to 5 tritium units. So basically anything beyond that 3 to 5 tritium units was pre-1963, probably 1950 water. The landfills operated in the 1960s, and they were the source of groundwater recharge even before the landfills were there. It was the highest area. It was a stand pit, basically. So because the groundwater on the outside of this colored rim is as far as the 1950s groundwater could move, and the 1960s groundwater was the only the start of the leachate, then that's as far as the metals could have moved from the landfill. So that helped a lot in helping us to convince the court where the extent of metals contamination from the landfill was. Here's another example of, and this time we're using oxygen 18 data. So this is the year before present and age before present. This material is from Edwards from the University of Waterloo in 1990. And what he did was he looked at shells and wood that had been age dated by carbon-14. So he knew how old his samples were. He was able to relate that to what groundwater would have been in the past. And he got this kind of function. And oxygen 18 is temperature related. And we know that for the past 10,000 years in the lower Great Lakes area, the temperature has been fairly uniform. But prior to 10,000 years ago, there was a very much colder area, the glacial periods. So this water here, anything with that kind of oxygen 18 concentration, will be really old water, thousands of years old. This type of signature in oxygen 18 will be a lot younger. So how can we look at a site and determine what's going on there? This is data in an area where there's a 30-meter thick till unit over the aquifer. Some of this area was considered for domestic waste. Some people even talked about storing nuclear waste in this clay zone. And the question was, how quickly could the water move through this clay material? So again, you see the plot that Edwards got for precipitation. The red squares are from a graduate student I had who was looking at the distribution of the oxygen 18 in the pore water, and he found some very old water at depth, and here's the depth over here. So below 20 meters below grade, the water was tens of thousands of years old, or 10,000 years old. Another graduate student, Andrew Ainsley, in the blue, found less definite old water at another site, but definitely the site that Ibrahim looked at, the water was old and could have been used at least for a regular landfill and not worry about impacting the groundwater below. So I'm going to move a little bit into the groundwater chemistry area and look at some of the ways in which we could get information on the vertical extent of impact, the sources of impact, and so on quickly, and in some cases getting information that you can't use using standard techniques like drilling holes, sampling soil, and sampling groundwater. So we're going to look at briefly the MIP, the LIF, XSD. We're going to look at passive soil gas, and we're going to look at compound-specific isotope analysis, a different type of isotope work. So here again, we're at that site in Kansas. Remember, we have to move quickly here. There's plumes moving towards the city's water supply. We have 5 years to come up with a RAP, so we've got to get a lot of information quickly. So again, our GeoProbe and the GeoProbe's GeoProbe working in this residential subdivision. We're going down about 70 feet. We're using HPT to find where the permeable zones are, and SP16, which allows us to go down the GeoProbe rods and sample groundwater at distinct elevations. So in our rig in the background, we're getting the vertical distribution of impact. In the foreground, GeoProbe's rig is using membrane interface probe, and basically what they're doing is getting a vertical continuous record of impact, and the chemical, that target chemical, was trichloroethylene, a metal cleaning chemical. So this is another site where we were using MIP, and you can see they've got their GeoProbe here with rods that actually have a cable going through them. That cable allows the MIP probe, which is kind of down here, and it's got a carrier gas in it and opening to the subsurface. And basically the MIP heats up the soil in the groundwater. A carrying gas brings it up through the rods into the trailer here that they've got a lab, and they've got analytical equipment that will give them real-time volatile organic compound concentrations with depth. So you can get information fairly quickly with the MIP. Here's another setup. Again, we're back out in Kansas with the GeoProbe's rig, our rig in the background. And here we're doing it at a site where we have a monitoring well nest. So we're using this to calibrate, in quotation marks, our MIP and HPT investigation. So the MIP is one of the tools you can use. LIF, or laser-induced fluorescence, will allow you to find free product like gasoline or free product TCE in the subsurface. XSD, halogen-specific detector, also looks like this type of probe, and you would be able to detect high concentrations of chlorinated compounds like TCE. So again, we use a combination of these tools to quickly move vertically and laterally to put our arms around the locations of the sources and to define the extent of the groundwater plumes. I'm going to change gears here, and we're going to look at passive soil gas. So in some cases you can't drill because you're inside a building with a low ceiling, or there's reasons that you can't drill. And here what we're doing is drilling really small holes, 2 to 3 feet deep, and putting in passive collectors to collect gas that is given off by volatile organic compounds. And in this case, we're looking for impact from a gasoline release. And inside this tube, there's absorbent material that we would put into the holes that we drill, and we'd keep it in the ground for a couple of weeks. We'd do a grid, and the grid in this case here are these bluish triangles, and we'd get concentrations from all of those locations and be able to get a relative concentration map of gases. And in this case here, the one you're seeing is from Beacon Environmental. That's the lab we've been using, and they were looking at chlorobenzene. But you can look at chlorinated chemicals like TCE or PCE, or you can look at benzene, toluene, ethylbenzene, and so on, and get these maps and determine where sources are. You can determine whether you have two unique sources if they're separate. Here it looks like one source in this area, and then we could follow up with other types of techniques to characterize the site for our conceptual site model. And finally, I'm going to talk quickly about compound-specific isotope analysis. So before, when I was talking about isotopes, I was looking at water. Here, I'm looking at chemicals dissolved in water. So we could look at things like nitrates, determine whether the nitrates are organic or inorganic, meaning from fertilizer or from, say, livestock. And we can look at chlorinated solvents like TCE, PCE, and so on, or we can look at fuels like gasoline releases and determine, answer questions about them, because as these chemicals break down, in the case of the chlorinated solvents and fuels, there are definite directions in which they break down isotopically. So this is a sketch that I made to demonstrate what happens with TCE, and this isn't to scale and it's not exact, but it gives you an idea that, say if we start with TCE in a flask and it's got that's 7 light isotopes and 3 heavy isotopes. This might be isotopes of carbon or isotopes of chlorine. When these chemicals break down, the lighter isotopes prefer to go into the product, like TCE would break down into DCE and then vinyl chloride. Well, you preferentially have the lighter isotopes leaving. So as the light isotopes leave, the remaining TCE now has a higher ratio of the heavy isotopes, and this continues. So you would see a trend from lighter or one type of concentration to a progressively heavier isotope-dominated chemical. So under biodegradation, if we started off with TCE here, so we've got all of it being TCE, isotopically it would change as the TCE breaks down into its daughter products. And this is looking at the carbon isotopes that you would see by the time you're down to 0.2 of the original TCE left, the carbon isotopic concentration is much different from the original. And you would expect to see that progression in biodegradation. So along a flow line, you'd expect to see a heavier and heavier dominated TCE remaining, and the lighter isotopes would be going to the daughter products. We can do that in two-dimensional compound-specific isotope analysis. Here we're looking at TCE, but we're looking at chlorine isotopes and carbon isotopes, and both of them respond the same way with biodegradation. They tend to get relatively heavier, more of the heavy isotope as you're going in the groundwater flow direction, unless there's a second source. And if you have a second source, this trend will change. And that's what you're looking for. You're looking to see if you have one or more sources, or you're looking to see if biodegradation is occurring in the groundwater flow direction, and you can use that in determining perhaps what you're going to do for remediation. So we covered a lot of material. We talked about some new techniques and some recent techniques and non-traditional techniques, but the important thing is we want to get the conceptual site model right. And some of the approaches we've talked about can make the road to a robust conceptual site model shorter, less expensive, more exact, and more easily defended. Some of the approaches we've talked about can do things that traditional approaches cannot do cost effectively, like the tritium dating and the oxygen 18 dating and some of the gases and isotope work. You just can't do that with standard techniques. So I'm going to turn you back to Alan for a minute, and I appreciate your attention.
I was planning on using 4, but I'm starting to think now that 4 might not be, or 4 might be too many.
Mike, assuming you can hear me, I do have one question that was submitted, and it's a two-part question, and it's relating to the isotope analysis. So what do the regulators think about the use of isotopes, and then what is the cost for the isotope analysis?
Well, the isotopic work has changed with time, and when I was a student back in the 70s, it wasn't very common, but it is now commonly accepted. For example, wellhead protection programs use tritium to determine the extent of the water they want to protect. They basically age date by tritium, and it's found a lot in the EPA literature and state literatures and so on. So it's more acceptable, and especially when you need a whole host of techniques to prove somebody who is difficult to prove things to, it's very good. There's a range of costs. If you're doing oxygen 18 and analysis, you're talking about $50 a sample or so. Tritium is about $100 to $200 a sample. And then when you get to the compound-specific isotopes, the costs increase a lot. You're talking probably about $600 a sample. But when you look in the big frame of things, when you're talking about projects that cost hundreds of thousands to millions of dollars or court cases, that they're really not that expensive if the information you get helps you to prove your conceptual site model.
Okay, thanks, Mike. Just one last thing is I'll remind everybody, as you see on that screen there, there's both of our websites are dragon.com and dragon.ca. And as Mike mentioned early on, if you go to our blog page on either one of our websites, you'll find a link to this and any of the other webinars that we've done. We have them on our YouTube channel, so you'll be able to access those. Again, just go to dragon.com or dragon.ca and go to the blog page, and you'll find a link to that. So with no other questions, I want to thank everyone for participating today, and we hope to make this recording available on that page soon. And once again, thanks to everyone.